we're going to talk about the heavy symmetric top. The heavy top differs from the free top in that you switch on the gravitational field. Let me try to indicate that graphically. So here you have your top. Here you have your body fixed frame, which has its origin at the point where the top is fixed, as before. This point is generally different from the center of mass. So the center of mass is at a different location. Due to the symmetry, it will be somewhere on the figure axis, but it's generally different from the point where the top is fixed. And the distance, let me call the distance of the center of mass from the point where the top is fixed, let me call that S. Then we have the inertial frame, and we agreed that the inertial frame has its origin also at the point where the top is fixed. So this is the inertial frame here. And in contrast to the free symmetric top, there's now a gravitational acceleration acting on the top. And it's clear that as soon as the center of mass is displaced from the point where the top is fixed, this gravitational field will lead to an external moment of force. So in the Euler equations, the moment of force no longer vanishes. Let me call the angle by which the body fixed frame is tilted against the inertial frame. In particular, E3 prime is tilted with respect to E3. Let me call that angle theta. To tackle this problem of the heavy symmetric top, we go back to the Lagrange formalism. And our starting point is the Lagrangian, which is kinetic energy minus potential energy. Since we have a top which is fixed at a certain point, the only kinetic energy, type of kinetic energy that we have is rotational energy. So we have the rotational energy minus potential energy. The rotational energy is 1/2 angular velocity scalar product with moment of inertia acting on angular velocity. That's the expression that we had found for the rotational energy, minus the potential energy. Now the potential energy is the mass of the heavy top times gravitational acceleration times the height of the center of mass, and that is given by S, the distance from the fixed point, times the cosine of theta. It's perhaps a slightly unfortunate notation, but it's a standard notation, and therefore I didn't want to change it, but you should pay attention that this theta here and that theta are not the same. The theta with the hat on top, that's a linear operator, that's the moment of inertia, and the theta without a hat and without an index, that's the angle theta. Now, you remember from our discussion and several applications of the Lagrange formalism that the crucial starting point is always a convenient choice of generalized coordinates. And that's the same here. The simplicity of the solution depends strongly on a good choice of the generalized coordinates. And in the case of the heavy symmetric top, this is a set of 3 angles. And I'm going to show on the next page, I'm going to show these angles, introduce these angles. They are not an immediately obvious choice, and they have a special name. They are called the Euler angles. The angle theta that you see in the figure is already one of them, and then there are two more. So let me start with the inertial frame, E1, E2, and E3. Next, let's look at the body fixed frame. It has the same origin. Let's say this is E3 primed. And already we said, this is one of the Euler angles, the angle by which E3 prime is tilted with respect to E3, we call that theta. And this is one of the Euler angles. Let me indicate the other two basis vectors of the body fixed frame. Let's say this is E1 primed, and this is E2 primed. So it's again an orthonormal basis, and it's rotated in an arbitrary direction with respect to the inertial frame. Now let me indicate the plane, the two-dimensional plane that is spanned by the basis vectors E1 and E2 of the inertial frame. This is spanned by E1 and E2. Let me also indicate the plane that is spanned by E1 primed and E2 primed. This is spanned by E1 prime and E2 primed. So you have these two planes spanned by basis, the first and second basis vectors of the respective frames. And these two planes are intersect in a line. The two planes intersect in this line here. So this line here, this is the intersection of these two planes. Now, along this intersection, this line of intersection, we define a new vector, unit vector, this one here. And we call this vector EK. Now, this is a unit vector pointing along the line that's the intersection of the two planes. Now, this vector EK is rotated against E1 by an angle phi. And E1 prime, in turn, is rotated, or the angle between E1 prime and EK, in turn, I call psi. And these three red angles, theta, phi, and psi, are the Euler angles. These are the generalized coordinates that we are going to use. A few more words about this new vector, this green vector EK. It lies in the plane spanned by E1 and E2. That plane is perpendicular to E3, so EK is perpendicular to E3. EK also lies, because it's just in the intersection of the two planes, it also lies in the plane spanned by E1 prime and E2 prime. And that plane is perpendicular to E3 primed. So EK has the property that it's perpendicular to E3 And it's also perpendicular to E3 prime. It's perpendicular to both E3 and E3 prime. It can be written as a linear combination of E1 and E2, since it's in the plane spanned by E1 and E2, but it can also be written as a linear combination of E1 primed and E2 primed. Let me write both possibilities. Let me first write them down, and then I can try to show you that this is indeed the correct relationship. If you express Ek in terms of E1 and E2, this is equal to cosine phi E1 plus sine phi E2. You see that? Because phi is the angle between E1 and Ek is in the E1, E2 plane. So this is straightforward, that Ek can be written in this form as a linear combination of E1 and E2. If, on the other hand, we want to use as the basis E1 prime and E2 prime, then you see the angle between Ek and E1 prime, that is psi, only that now the direction of the angle is different. You measure the angle starting from Ek rather than E1 primed. So you have the same structure, but with a different sign. So you have cosine psi E1 prime minus sine psi E2 prime. So that's the other possibility of writing Ek. Now, we are not finished yet with the drawing. I have to indicate two more vectors. One vector is the vector product of E3 with Ek. Now, vector product of E3 with Ek must be perpendicular to E3, and therefore it must be in the E1, E2 plane, and must also be perpendicular to Ek. So approximately here. This is E3 vector product with Ek. And a last vector I would like to indicate is E3 prime vector product with Ek. That must be in the plane spanned by E1 prime and E2 primed, and again perpendicular to Ek. So these are the last two vectors. Okay, and one last relationship. E3 primed is in the plane spanned by E3 and E3 vector product with Ek. Why? Because E3 primed is perpendicular to Ek. So E3 prime must be in the plane that is perpendicular to Ek. Now the plane that is perpendicular to Ek is spanned by E3, because E3 is also perpendicular to Ek, and E3 vector product with Ek, which is also perpendicular to Ek. So it must be possible to write E3 primed as a linear combination of E3 and E3 vector product with Ek. Since the angle of E3 prime with E3 is theta, it is possible to write E3 prime as cosine theta times E3, and then due to the orientation of E3 vector product with Ek, it must be a minus sign, so it's minus sine theta times E3 vector product with Ek. So these are three relations between the vectors in this drawing that we are going to use in the following. Now let's work with the Euler angles, and remember in the Lagrange function we have the expression for the rotational energy, and in there is the angular velocity omega, and our immediate goal is to express the angular velocity vector omega in terms of the Euler angles, so that afterwards we have the Lagrange function as a function of the Euler angles. And let's exploit the various relations that I had noted on the drawing. The first relation, or one of the relations, was that Ek could be written as cosine psi E1 prime minus sine psi E2 primed. Let's take the time derivative of that. So let's calculate Ek dot, and simply by product rule you get minus sine psi psi dot E1 primed. Let me save the E1 prime dot for later. From the second term we get minus cosine psi psi dot E2 prime. Yeah, and then we have terms with E1 prime dot and E2 prime dot. Now the EI prime dot, this is, as always, this is omega vector product with EI. And this holds for both E1 prime and E2 prime. So we can simply replace that and write that as omega vector product with Ek, because then we have still the cosine psi and the sine psi in front, and we can write the linear combination of E1 prime and E2 prime as Ek again, and so we just have omega cross Ek. Now let's look at sine psi E1 prime plus cosine psi E2 primed. This is another relation that I did not write on the previous page, but you can convince yourself geometrically that this in turn is E3 prime vector product with Ek. Perhaps you want to see that on the previous page. Psi is the angle between Ek and E1 primed, and it's also the angle between E3 primed cross Ek and E2 primed. And you can view Ek and E3 primed vector product Ek. They are orthogonal on each other, and they constitute a basis that spans the E1 primed, E2 primed plane, and so does E1 prime, E2 prime. There's also an orthonormal basis in that plane, and that basis is rotated against the former basis by the angle psi. So you have the angle psi also here. And this motivates why this linear combination of E1 prime and E2 primed, that this is just equal to E3 primed vector product with Ek. So you can make this replacement in blue, and then you add the omega vector product with Ek, and you can summarize that as omega minus psi dot E3 prime vector product with Ek. So this is one equation of motion for Ek. We could also have started from the relationship Ek is equal to cosine phi E1 plus sine phi E2 and take the time derivative of that. Then we find that Ek dot equals minus sine phi dot E1. Now in this case there is no E1 dot because this is the inertial frame and it doesn't change in time. And we have plus cosine phi dot E2. If we look here at this linear combination minus sine phi E1 plus cosine phi E2, this equals E3 vector product with Ek. Again, you can convince yourself by looking at the figure, you can convince yourself geometrically that this relationship holds. So, in sum, Ek dot can be written as phi dot times E3 vector product with Ek. So we have two different expressions for Ek dot. Of course, they must be equal. So whatever is on the right-hand side must be equal. Let's subtract equation number 2 from equation number 1. Then on the left-hand side we have 0, Ek dot minus Ek dot. On the right-hand side we have omega minus psi dot E3 prime minus phi dot E3, and all of this vector product with Ek. This implies that whatever is inside the bracket must be parallel to Ek, must be proportional to Ek. So this implies, in other words, that omega, the vector omega, must be equal to psi dot E3 prime plus phi dot E3 plus some factor alpha, which we don't know yet, times Ek. So this is yet to be determined. Now, let us use the third relation that we noted on the previous page, namely that E3 prime can be written as cosine theta E3 minus sine theta E3 vector product Ek. And let's take the time derivative of that. So we have E3 prime dot. Again, E3 is part of the inertial frame. Its time derivative vanishes, it's constant in time. So we only have time derivatives of theta and of Ek. We also know, on the other hand, that the time derivative of E3 prime, that's omega vector product with E3 prime. That's the usual relationship that we have, right? So this is omega vector product with E3 prime. But this must also be equal the time derivative of the right-hand side on the previous line. So let's see what that gives. This gives minus sine theta dot E3 minus cosine theta dot E3 vector product with Ek minus sine theta E3 vector product with Ek dot. Now we have a combination here, sine theta E3 and cosine theta E3 vector product EK. This linear combination gives E3 prime vector product with EK. Again, you should have a careful look at the graph, at the drawing, at the figure, and convince yourself geometrically that this is the case. And the EK dot, for this we use result number 2. We use that this is phi dot E3 vector product with EK. So what do we have? We have on the left hand side, we have omega vector product with E3 prime. On the right hand side, we have a minus theta dot E3 prime vector product with EK. And then we have a minus sine theta phi dot, and then we have a triple vector product. We have E3 vector product with E3 vector product EK. But this is equal to minus EK. So E3 cross, in brackets, E3 cross EK, this equals minus EK. So this gives then, this gives this whole expression a plus sign, and this gives sine theta phi dot EK. All right, you remember that what we have yet to do is, up there we expressed omega as a linear combination of E3 prime, E3 and EK. We have yet to determine the coefficient alpha in front of the EK. So now what we are going to do is we are going to use this result here with the star and insert this form into the last equation that we have. So we insert the star, and then we get on the left-hand side psi dot E3 prime vector product with E3 prime plus phi dot E3 vector product with E3 prime plus the unknown alpha EK vector product with E3 prime. So this is the left-hand side. This must be equal to, and now let me just exchange the order and write sine theta phi dot EK minus theta dot E3 prime vector product with EK. On the left-hand side, E3 prime vector product with itself is 0. E3 vector product with E3 prime, this gives a vector which is orthogonal to both E3 and E3 primes. The one vector we had in our drawing which was orthogonal to both E3 and E3 prime was EK. So this result is proportional to EK. The proportionality factor is just the sine of theta. So this is sine theta times EK. But you see that then we have sine theta phi dot EK. This is exactly the same term that we also have on the right-hand side. Yeah? So this term equals that term. And we are left with the equation alpha times EK cross E3 primed equals minus theta dot E3 primed cross EK. We can, on the right-hand side, we can exchange the order in the vector product. This gives us the minus sign, so we get rid of the minus sign in front of the theta dot. And therefore, we can identify, finally, that alpha must be equal to theta dot. So we have the alpha, finally. So, this was a little bit tedious, I agree. But the good thing is that now we have a rather simple expression for omega in terms of the Euler angles. We can write omega equals psi dot E3 primed plus theta dot EK plus phi dot E3. Now this is a very useful, simple representation for omega, and this is the key reason why the Euler angles are such a convenient choice for the generalized coordinates. We can now take this further. We can write the EK as the linear combination of E1 primed and E2 prime. And we can write the E3 as a linear combination of E3 primed and E3 primed vector product with EK. And then again we can write EK as a linear combination of E1 primed and E2 primed. So this gives then cosine theta E3 primed plus sine theta cosine psi E2 primed plus sine theta sine psi E1 primed. So all together and in the correct order of the basis vectors, this is phi dot sine theta sine psi plus theta dot cosine psi E1 primed plus phi dot sine theta cosine psi minus theta dot sine psi E2 primed plus phi dot cosine theta plus psi dot E3 primed. So now we have omega represented in the body fixed frame as a linear combination of the basis vectors of the body fixed frame. And we can identify this here. This must be the component of omega, the first component in the body fixed frame. This here must be the second component, and this here must be the third component of omega in the body fixed frame. So we have finally formulas for the components of the angular velocity vector in terms of the Euler angles. And this we are now going to insert into our formula for the Lagrangian. The Lagrangian, remember, was rotational energy. The rotational energy can be written very simply in terms of the components of omega in the body fixed frame. Since the body fixed frame, we said, is an eigenbasis of the moment of inertia. Because then the rotational energy is simply eigenvalue theta 1 omega 1 prime squared plus eigenvalue theta 2 omega 2 prime squared plus eigenvalue theta 3 omega 3 prime squared. That's the rotational energy minus the potential energy, which was mgs times cosine theta. Here we can use the symmetry. These are equal by symmetry. And we can use the expressions for the Euler angles, for the angular velocity components in terms of the Euler angles that we found on the previous page. And then you obtain the Lagrange function as a function of Euler angle theta, and then the time derivatives phi dot, psi dot, and theta dot. And it turns out that the dependency, there's no dependency on phi and psi. So phi and psi are cyclic. The Lagrange function does not depend on phi and psi. It only depends on theta and on the time derivatives of all angles. And it has the form eigenvalue theta 1 over 2 times theta dot squared plus phi dot squared sine squared theta plus eigenvalue theta 3 over 2 psi dot plus phi dot cosine theta, and the whole bracket squared, minus the potential energy, which is mgs cosine theta. So this is the Lagrange function in terms of the Euler angles. So we spent a lot of time finding the correct generalized coordinates. That was basically that's the main piece of work that you have to do here. Now we have the Lagrange function in terms of these generalized coordinates, and then we can start our usual machinery, look at conservation laws, derive equation of motion, and so on.